And so in this presentation, I'd like to talk about an ongoing work with Maxime Dallery, who is a PhD student at UFC, Virginie Erlacher, who is in the room with us, Alexei Luzinski, who is a professor at UFC, and Etienne Pollack, who is now a postdoc at École des Ponts. And so first I'd like to give a small apology. So I know the title of the workshop is New Mathematics for the Exact Scale. So my talk will be more on the new mathematics side than on the exact scale. However, I really hope that the ideas that I present in there can really be scaled to large systems in a near future. Okay, so in this talk, so I will focus on electronic structure calculations. So I have kind of the same picture as Gabor, so he talked a lot about this. So what I will just say is that in this talk, I will really focus on this extreme left part of the figure here. So wave function methods and density functional theory. So these are the kind of extremely expensive methods, but also highly accurate methods that models the electrons. In the molecular systems or the material system that you're looking at, there exists a large variety of models, from the Schrödinger equations to Hartree-Fock density functional theory and a lot of other ones. And Gabor also kind of motivated the need for efficient electronic structural calculation methods, since he showed that 40% of the supercomputer use goes into simulating DFT and similar methods. Okay, so in this presentation, I will focus just on the ground state problem, which is the problem of minimizing the energy of a given system, and I will be in the Born-Oppenheimer approximation, so that the molecular system is described by M nuclei indexed by their positions R in the space, and then the electrons will be described by a wave function or orbitals in DFT. And so the problem we are looking at is an energy minimization problem, here where H of R is the Hamiltonian of the problem and has several parts. So one part with a Laplace operator coming from the kinetic energy, one part modeling the interaction between the electrons and the nuclei, and the electron-electron interactions involving Coulomb potentials. And so if we write the first order Euler-Lagrange equations of this problem, then we find an eigenvalue problem to solve H R psi equal E psi, and H R is the same Hamiltonian here of the system. And so, in general, this problem is parametrized by the positions of the nuclei in the system. And so, what I want to try to do in this presentation is to approximate the full set of solutions for some nuclei positions which live in some set of configurations that I choose. Okay, and so to do so a bit rigorously, I will even simplify the problem. I will simplify the problem even more and consider really a toy problem in 1D. So the energy functional is just this, and so here, if we look at the eigenvalue problem, maybe it's easier to see. So here, this is the Laplace term, so just a second derivative, and then the potential I am considering consists of Dirac delta potential centered at the nuclei positions and with charge Zm. And so the reason why we chose this particular potential is that the solutions of this eigenvalue problem have the same regularity as you would get in 3D with Coulomb potential. And also, we know analytic solutions for this equation. So the eigenvector, so the lowest lying eigenvector in this case, is a linear combination of Slater functions centered at the nuclei parameters and with some coefficients here, which can be easily computed. Okay. And so typically this is what the solutions look like. So this is for examples with 2 particles. This is with 3 particles. And so the aim here is really to manage to efficiently approximate all the solutions when the positions of the nuclei vary with the computation of only a few solutions. So in a way, we want to find a representative set of solutions from which it will be easy to reconstruct all the solutions in this set as efficiently as possible. Yes?
When you construct your representative set, are you going to fix positions, or are you going to look at collections of fixed positions?
So I will consider as large as possible collection of positions. Okay, and so this idea of finding a good representative set of solutions is really close to what is called reduced order modeling, and in particular the linear reduced order modeling. So I will start my presentation by describing this a little bit and showing why in our case this doesn't fully work. And the way we will get around these problems will be to introduce some approximations using optimal transport. And so I'll talk a little bit about this afterwards, and then I'll describe the practical strategies that we have put in place to approximate these solutions. And if I have time at the end, I'll talk about a little bit about another application for this. Okay, so in the context of linear reduced order modeling, the problem is in general parametrized PD, so exactly as like what we have in here, and then it's parametrized with some parameters. And this equation needs to be solved many times. So this is exactly what happens if you run ab initio molecular dynamics. You change the nuclear positions, and then you solve the electronic structure calculation at each step. And so in the linear reduced basis method, so this method is kind of separate into 2 parts. So one part is called the offline part. So this is where you put a lot of computational resources, but you do this kind of in advance. So in the, let's say, the machine learning community, this would be the training phase. And then in the online part, you want to have a way to very efficiently compute the solutions for a new parameter R. And so the way it works is that, so in general, in the offline part, what you do is, so first you generate a training set of solutions, and then you will select the good solutions with a greedy algorithm. So you start by selecting one parameter, and then at each iteration, you will select the parameter so that the solution is the worst approximated by the previously selected solutions. And so this gives you the new one, and then, and so on, you collect all the snapshots that are least well approximated. And then once you have this, what is called the reduced basis, in the online part, what you do is that when you want to compute the solution for a new parameter, you solve the partial differential equations on the basis of the selected solutions. So in a sense, you have a partial differential equation to solve, but on a very small space, because the snapshots represent well the space of the solutions.
Can we think of this as time binding, but with numerically computed atomic orbitals?
Something like that, except that you would have a linear. You would have to have in that framework, you would have a linear representation of the solution with respect to the others. And so in time binding, I would say you would move somehow the basis functions. Okay, and so this is used a lot nowadays in the industry. So This is, for example, this has been very successful in continuum mechanics or for thermal equations. So there is another project I'm working on with the French Atomic Agency on a neutronic problem. And so in that case, basically, we have a nuclear core which is parametrized by, so the kind of the nuclear core is divided into few cells where you put the uranium. And so this gives you different parameters for your equations. And so basically, you need to compute the solutions for many different possible placing of the uranium. And so for this reason, we need kind of a quick way to solve the problem, which is an eigenvalue problem. And so what we observed for this case is that if we select something like about 100 basis functions, so 100 snapshots, then we get very accurate solutions when we change the parameters in the nuclear core. So like with a section of the order of 100 basis functions, we managed to have a satisfactory approximation. But the real key point here is that the solutions should be well approximated by linear combinations of the few solutions. And so this is kind of, this translates into a notion that is called the Kolmogorov n-width. And so basically this quantity that is defined here tells you, characterizes how well a set can be approximated with linear space of dimension n. And so if this Kolmogorov n-width decreases very quickly, then the method has a chance to work. If this Kolmogorov n-width decays very slowly, then there is no way that we will be able to represent all the solutions with a few given snapshots. And a typical example where it works is when one considers an elliptic equations where this AR, so this is our operator that is parametrized by R, has an affine representation, so which means that it can be written as functions that depends on the parameters times some fixed continuous operators. And in that case, it can be proved that the Kolmogorov n-width decay exponentially. And so in that case, we know that the method will work pretty well. Okay. There are examples where this works not as good. So for example, if you consider one-dimensional transport equations and that your solution is kind of a step functions that moves around in time. So you have the solutions will be these step functions. And so in that case, it's possible to prove that the Kolmogorov n-width decays as slowly as 1/√n, which means that we won't be able to efficiently approximate the solutions with linear combinations of other functions. But this is kind of understandable. If you take the rightmost snapshot here and you want to approximate it with the one on the left, there is no way it can work. And so in electronic structure, we have kind of the similar problem. So if you translate, if you take just just one atom and then you translate it in space, your solution gets translated as well. And so we will have the same problem as for the transport equation. And so what we showed with Maxime, Virginie, and Alexei is that in the case of this toy problem, we can actually give an estimation of the Kolmogorov n-width, and it doesn't decay very slowly. So we get a factor n to the -3/2, which is not much. Okay, and so So for this reason, we kind of need to find an alternative. So we need to find a good nonlinear transformation which will at least deal with these problems of the translation. And here, this is why we thought about considering optimal transport. And just because, so for example, here we have two atomic solutions, and here in red you have the barycenter in the optimal transport sense, and you see that you go smoothly from one solution to the other, but just translating the solution. Yes?
When you were computing your n-width bounds, the lower and the upper bound, you were taking advantage of the fact of those translations, and those were the things that were causing the n to the minus some power growth. So I just wondered what, again, was the intuition behind the bounds that you got?
Behind the bounds here? The 3/2, I couldn't really explain apart from saying that, I mean, we would get through the proof and that's kind of the exponent that goes out.
Yeah, what was the underlying intuition, though, for getting a bound that had a negative exponent with respect to n, the number of basis elements?
Oh, but the negative exponent is because if you increase n, then you increase the size of the basis, and you expect that you will approximate the set of the solutions better than with a smaller n. So this should be a decreasing function in n. Yeah.
Fair enough. Yeah. But the exponent you have is not the one you want.
Yeah. Exactly. Yeah. Okay. Okay. So since I'm assuming that many of you don't know many things about optimal transport, I'll talk a little bit about this. And so just to give you a few kind of a description of the few objects I will need in the following. So the first thing I will need is what is called the Wasserstein distance. And so basically it allows to compare probability distributions. And so it is defined as this, as the infimum over this, what is called transport plan of this cost function here. And so here is an example. So if you have one probability distribution here and another one here, the infimum over this set here will be this line here. And what this says is that kind of the mass that is here will be transported in this part of the space. Okay, so that's kind of the first thing we need. So that's a distance, a notion of distance. And the second thing is we need a way to interpolate between different probability distributions. And this is the notion of Wasserstein barycenters. And so the problem here is a minimization problem. So so this is for defining the barycenter between q probability measures and with some coefficients t. And so this is defined as this infimum, this minimization problem. And the intuition behind this is that if instead of this Wasserstein distance, you put the Euclidean distance, then the solution to this problem is just the standard barycenter, just the combination of the TQ times UQ. So this is kind of an extension of this definition of barycenter for this specific distance. And in practice, to find this barycenter, one solves this kind of complicated, what is called multi-marginal optimal transport problem, which is kind of a generalization of the problem you solve to compute the Wasserstein distance, which involves a multidimensional transport plan here, which depends on the So it should be Q on the different probability measures that you consider. Yes?
Why do you want to define the barycenter in terms of the W2 measure and not just the Euclidean distance between the two?
Because if you look at the barycenter in terms of the Euclidean distance, you will get lambda times the first one plus 1 minus lambda the other one. And so this won't shift the peak. So the peak won't go from one place to the other. You will have two peaks that kind of get compensated. Okay, and
which means that on the same example, when you have these two measures, and if you do the barycenter in terms of W2, you will have something with a bit of shape.
Yeah, so this would be exactly the Wasserstein barycenter between these two functions. Okay, so I know these definitions are a bit abstract, so I'll try to give two examples where these quantities can be easily computed. And so the first one is the one-dimensional case. So if you have probability measures in R, then there is an explicit way of writing this Wasserstein distance as an L2 norm of the inverse cumulative distribution functions. So there is an explicit way of writing this, and kind of similarly for the barycenter, the inverse cumulative distribution function of the barycenter is the convex combination of these inverse cumulative distribution functions. So just to give an illustration, so here we have two probability measures, and then we can compute the cumulative distribution functions here, the inverse cumulative distribution functions here, and then when we do a convex combination of these two functions and we map them back to have the cumulative distribution function, this gives us this barycenter here, which is the Wasserstein barycenter. Okay, and so the second example that is really nice is when one considers location scattered transforms. So basically, you take one measure and then you translate it and you dilate it as much as you want. And so, for example, if you take one Gaussian, you translate it and you dilate it, then you generate all possible Gaussians. So this is the location scattered transforms. And so in that case, the Wasserstein distance can also be easily computed as it only depends on the means and the covariance matrices of these probability measures. And the Wasserstein barycenters can also be explicitly computed. So typically, the mean would be the convex combinations of the means, and then the covariance matrix satisfies a kind of a nonlinear equations, but which can be easily solved using a fixed point algorithm. And so this is a typical example. So if you have three Slater distributions here, and then you compute the Wasserstein barycenter here, the center would be kind of in between the three centers, and then the covariance matrix will be something in between the covariance matrices here. Okay. Yeah.
So does this work so you presented it for Gaussians, but it works for any kind of family of distribution? So if I just take some probability measure, then I can do this scattering transform, and then I always have the same?
Yes. Yeah, if you generate them with these kind of locations, so translation plus dilations, then in that case that works. So for example, I mean, in what I'm interested in, Slater will work, Gaussians, but also, I mean, if you have something, any kind of elliptic distribution will work. Okay. And so now if I go back to my original 1D toy problem, then if I want to estimate the Kolmogorov n width for this Wasserstein distance. So what I can say is that since this Wasserstein distance can be written as an L2 norm of the inverse cumulative distribution functions, then I can just define it as the Kolmogorov n-width for the L2 norm and transforming the set of solutions. And so in that case, what we proved is that the Kolmogorov n-width decays at least as fast as n to the minus 502, so which is not great, but still better than the minus 3½ that we got before. Okay. Now I would like to kind of comment on the numerical cost of computing these Wasserstein barycenters. So here, this is the kind of the numerical problem that is involved in for computing the Wasserstein barycenter between those two distributions. So what we would do in general would be to kind of discretize this on a grid and then have a discrete problem that depends on the size of the grid. So the unknown will be will be a matrix of size n grid times n grid. And so then we would have a constraint optimization, convex optimization problem to solve with this dimension. The problem is that this is computationally quite demanding, especially if, so this is a 1D example, but if you go to 2D, then if you want a kind of the same type of discretization, then you get n grid to the square here. And so this very quickly gets very expensive. And so to give an idea, I think this, to compute this, it's the order of, I don't know, 10 to 30 seconds. It depends on what kind of parameters you take, number of iterations and so on. But if you go to 2D, then you are quickly of the order of minutes, and you cannot imagine to do that in a kind of in an online phase. And another problem is that to kind of accelerate the algorithms, there are some smoothing involved, and so it gives something like some smoothing here in the barycenter, which is something that we wouldn't like to see. And this gets really, really worse when we want to compute barycenters between many solutions. Okay, so kind of the way around that was proposed in a paper by Julie Delon and Agnès Zollner in 2020. And so the idea is kind of to consider a similar optimal transport problem, but to define a modified metric which will apply for mixtures of probability distributions in some class of functions. So for example, Gaussians or Slater, and then to say that this modified distance will be the solution of this minimization problem, where the cost function here involves the Wasserstein distance between the individual components of the distribution, and so then the unknown here is of size the number of components in the mixtures, but the kind of the problem, the mathematical problem involved stays the same. Okay, so this is typically what is obtained. So this was the optimal transport plan that we had before, and this is the kind of the modified optimal transport plan. And so what happens is that basically you consider affine transformations between the here, and so yeah, the transport map is kind of approximated by these affine lines. And a nice point is that the number of components in this problem and the non-zero components here in this minimization problem cannot exceed so j plus k minus 1, so the sum of the number of components, while the side of the matrix is j times k. So in some sense, it stays, the number of non-zero components stays linear, even if we have a problem that looks quadratic. Okay. And so, so then we can kind of define a similar things for the mixture Wasserstein barycenter, and so so basically replacing the Wasserstein 2 distance by this mixture distance. And so what is nice is that it kind of compares. I mean, we don't have this smoothing that we had for the the true Wasserstein barycenter, and also an interesting feature is that the computational cost is independent of the dimension. So if now we have Gaussians that are in 3 dimensions or in n dimension, since the computation only involves these Wasserstein distance here, which we can compute for any dimension because of the, I mean, at least for Gaussians, then the problem will only depend on the number of Gaussians that need to be considered for in the mixture, and not on the dimension. So this is kind of really nice. And another thing that is quite nice is that so we have a kind of a formula for the barycenter, which write as a W that is solution to a multi-marginal problem. So I don't want to go into the details, but so this is kind of hard to get. But then if you have a new T, then you don't need to recompute those. And so you only need to compute the Wasserstein 2 barycenters between individual components. And so this, once again, is really quick to get. Okay. And so to kind of finish to answer your questions, so with Virginie and Nathalie Nouaime, we kind of we generalized the kind of the Gaussian setting to consider a larger type of probability distributions. And so we kind of went through the mathematical properties that you need to define such a mixture distance. And computationally, what is really important is that the barycenters between individual components can be computed efficiently. And so that's kind of one key. So it works for elliptic distributions. All the locations scatter atoms. And another nice feature is that you can also incorporate some group invariance into the individual atom distributions, so that you don't see the kind of the group complexity on the whole thing. So this is just a kind of a picture of a barycenter in this mixture sense for Wigner semicircle distributions. So something that has compact support, and for which we can do exactly the same as for Gaussians. Okay. So just to finish on the theoretical aspect, so the last thing we wanted to kind of look at theoretically is what we can do for these. I mean, if we kind of define Kolmogorov n with respect to this mixture distance, the problem here is that we don't have, as for the Wasserstein case, kind of an interpretation with a different an L2 distance in a different space. So we kind of really need to define a nonlinear Kolmogorov n width. And so what sounded natural to define was kind of the minimal, so the best set of n functions you choose, and then you look at the maximal error on the set of configurations of the approximation. I mean, the distance between the solution and a barycenter in the mixture sense between the previous solutions. Okay, and so what we showed is that if you have a system with 2 nuclei with identical charges, then this mixture, this Kolmogorov n width is 0 from n larger than 2. So basically, if you have 2 solutions, then you can exactly fit these solutions using a mixture Wasserstein barycenter. It only works because the 2 nuclei have identical charges. So in that case, we can exactly represent this, all the solutions in the manifold. Yes?
Should this be obvious? How can this be true for a nonlinear problem?
Oh, no, it's a linear problem. It's a linear eigenvalue problem. Yeah. No, it's one electron and one d nuclei. Yeah, it's it's linear. And we know explicitly the solutions, so yeah, no problem. Okay, so now I'd like to discuss a little bit the kind of the computational aspects and how we get a nonlinear reduced basis methods. And so the idea will be exactly the same as for the linear reduced basis methods. So we will have an offline part where we want to select the wisely chosen parameters and corresponding solutions. And so to do that, we start by selecting two parameters for which the solutions are as far as possible. And then at each iteration, we will select the solution that is the least well approximated as a barycenter of the previous solutions. And so, and then in the online part, we will compute the solution for new parameter as a barycenter of the previously selected snapshots. And so, so basically, the linear combination is just replaced by a barycenter in the sense of this norm. Okay, so and just to give some detail about this greedy algorithm, so the main part here is at each iteration to solve this problem of finding the worst case of the best possible approximation in this Wasserstein 2 mixture, Wasserstein distance. And so I don't want to go through all these equations, but so what's important is that when we solve this problem, a lot of things can be written down explicitly. And what we get at the end is that this problem can be written down as kind of this thing here, so which is a non-convex optimization problem to solve. So it's not great, but still it can be really easily formulated. And there exist different methods to solve such problem. Okay, and so that was for the offline part. Now for the online part. So the idea is that since we want to optimize for a new configuration, we want to optimize the solution as a barycenter of previously selected snapshot. We have somehow a nonlinear problem to solve, but in low dimension.
In the offline part, sometimes in this kind of things, there is a posteriori error estimator which is used.
Yes, we don't have that for now at all. This is kind of in the perspectives, but for now it's really, we are not that far. Okay, so to be on the online algorithm, what we want to do is basically to minimize the energy to find the best possible solution in this set of barycenters. And so to do so, so this is kind of an example of a profile of energy when we have selected two snapshots. And what we see is that they are kind of sharp local minima. So this is also not great on numerical point of view. So what we do is that we use a quasi-Newton method and we start at different points so that we don't miss the global minimizer. Okay, so I'd like to kind of finish this part by presenting a few numerical results. So basically here we we take a system with two nuclei with two different charges. We take about 300 solutions in the training set, and then we look at the error decrease when we select the the snapshots in the greedy algorithms. And so what we see is that, so for example, for the mean error in red here, we gain something like about 2 to 3 orders of magnitude in the error by the selection of between 10 and 15 functions. So this looks really encouraging. So of course, the cost of computing that is way higher than in the linear case. But still, there is hope if we manage to kind of accelerate this greedy algorithm to have something that is really efficient, because we don't really need many functions to obtain an approximation that is good. Okay, so these are kind of the first 8 selected basis functions. And so what you see is that, so first we select the blue one, then the red one. So these are the ones that are further apart. And then we will select the green one, which is kind of in the middle, and then we will kind of fill the space so that we approximate as best the possible solutions. Okay, and so this is an example of the projection of a random solution for different sizes of bases. And so the red one is if we only consider 2 functions, then 4 functions, and we see that here in this specific case, if we take only 6 functions, we don't see the difference between the approximation and the true solution. Okay, so now this is for the online part. So here we minimize the energy for all of the snapshots, and we see how the energy error decreases. And so once again, here we see that we gain a factor of about 2-3 orders of magnitude, and with only something like 9 basis functions. So this is this is really encouraging in terms of accuracy. And so just a side remark. So here, in the online phase, we chose to minimize the energy because this is what we are interested in the end. So we thought that it would be kind of more relevant to optimize the energy. We see, however, that the solutions, at least when we don't have so many functions, that the solutions obtained with the energy minimization and the projection for the barycenters can be different. So this is the example for with 3 functions. So then I run the same test with 5 functions. We don't see the difference anymore. So kind of when we increase the size of the basis, it seems that the differences get smaller. And just to finish, I'd like to show a little extrapolation example. So it's not much, but so in our training set we had solutions with nuclei positions between 0 and something like 3, and here I tested with 4, so not so different, but still outside of the training set. And so what we see is that here with only 3 basis functions we get okay, so this is wrong. Okay, so in red we have the energy minimizer on this set of 3 functions. And we see that the solution seems a bit far, but still if we look at the energy, it's closer to the exact energy, which is here minus 0.6, than the green line here, which is not the energy minimizer, but which is the projection. Okay, and here this was what we obtained with 5 functions, and so what we see is that we get really close to the exact energy, and the solutions look reasonably close to each other. Okay, so just a few comments on these methods. So I would say some of the key points in this work is that all what is done is independent of the underlying dimension of the space, which is really important if we want to hope that it can scale to 3-dimensional systems. However, the problem size depends on the number of functions in the mixtures. So if we have large systems, we need to deal with the fact that there will be many more so Slater or Gaussian functions than just the two that we had here. Another limitation of this work at the moment is that for the theory to work, we need to work with probability distributions. And so this work, in this case, where we have the lowest eigenstate, which is positive, so that we can renormalize with respect to the L1 norm. But in general, if we consider the eigenstates, they are not necessarily positive, so there is no way we can define such distances. However, we can consider the electronic density, which can be rescaled at least to be a probability distribution. Another kind of main limitation at the moment is that when you compute barycenters between many different functions, then you need to solve a multi-marginal optimal transport problem, which is very difficult. But we have some hope with new algorithms that are coming in. So, for example, the GenCall algorithm that was proposed very recently by Gerald Friesike and Maximilian Penka. And so in the future, to make this scalable to larger systems and to real molecules, so in some way, ideas would be to consider not only Gaussians, but Gaussian time polynomials to get closer to what we get out of computer codes. And then also to kind of not consider the density, but consider the orthogonal projectors directly. And then in that case, there is a theory called quantum optimal transport, which could kind of help us in deriving such kind of similar theory in that framework directly for orthogonal projectors. And then another thing I haven't talked about, so in what I showed here, everything is done to kind of have the best possible solutions at any computational cost, let's say. So the projections are expensive, the energy minimization is a bit expensive, but at the end we guarantee that we find the optimal solution. Another way would be to say, okay, we just want to compute barycenters, and so then we learn the map that gives us the parameters for computing the barycenters, and then once we have the map, it is very efficient to compute the barycenters. So this would be kind of a way to gain a lot in computational cost and probably lose a bit in accuracy. Okay, so I guess I'm kind of at the end of my time. So okay, so then I'll just mention a little bit about a different problem, so which is kind of the approximation of the map from the density to the pair density. So here the context is really looking at the Schrödinger equation and at the electronic part of the energy, which, so maybe a bit quick, which is here and can be explicitly written as a function, as an integral depending on the pair density, where the pair density is defined as the modulus square of the wave function integrated out over all variables except 2. And so, so the idea here is really just to, in what I will show in the next few minutes, is just to try to have an efficient approximation of this energy. So. Okay, so this is a kind of a 1D 2 particle systems for different potentials. So these on the top lines are the potentials, and then we see the electronic density and the corresponding pair density. So we see the pair density nicely dissociating. And so then if we want to, so then what one kind of typical approximation would be to do LDA. So I know there are lots of better approximations to the energy, but for LDA, we can derive a ρ2 such that the formula for the electronic part corresponds to what is given by LDA. And so what we see is that this gives this kind of approximation here of the pair density, which looks really, really far from the exact one. And so, and also the order of magnitude. So this is the relative error on this quantity. And so it goes from 0.3 to 0.07 when the system dissociates. And so what we tried here was really to do something simple. So first, we just decided to kind of compute a Wasserstein 2 barycenter between this example here and this one, and see how well the approximation is. And so this is what we get here. And so what we see in terms of the error is that we gain kind of 1 or 2 orders of magnitude in the accuracy. So this looks pretty good. But then, as I said before, so the computational time for this single barycenter is of the order of a few minutes. So this is really not possible to imagine to do something like that for 3D systems and for systems with more particles. And so what we did very recently was just to try to first fit the density with Gaussian functions, and then so fit this one, and then fit the one on the right, and then to compute the mixture barycenter between those, and then to see what we get. So if we look at the pair density, it kind of looks even a bit better than the Wasserstein barycenter. Although we kind of see that the shape here of the bumps are a bit too round compared to the exact one. But this is kind of due to the parametrization with the Gaussians, because here we only really use 2 Gaussians to fit this. So this is really low dimensional. So I guess that if we improve the fit here, we could get more accuracy. But still, if we do this kind of very simple fit, we get an error that is at least 3 times better than what we get with the LDA. It seems surprisingly a bit less good than the true Wasserstein barycenter. But so this is something where we need to continue some work to have like meaningful numbers. Okay, and so with that, I'll finish. Thank you very much for your attention.